In this module, we turn our attention to sampling, a critical component of research design. It may seem like a dry and somewhat technical topic, but it is in fact vitally important, because without an appropriate sampling plan, all our efforts in defining the problem and designing the questionnaire or experiment will come to naught. We start by looking at some terms used in sampling. We then consider some basic sampling procedures and discuss their limitations. Let's refresh our memory on some of the terminology of sampling. The sampling frame is a list of the target population members or sampling units. A sampling unit can be a person, a household, a firm, a block, a zip code, etc., and represents the level at which we draw the sample. There are various sources of sampling frames: commercial suppliers of mailing lists, magazines that sell subscriber lists, credit card companies that provide lists of card holders, the U.S. Postal Service that provides street directories, telephone companies that publish directories, and so on. The sampling procedure is the process by which we draw a sample from the sampling frame. There are two types of sampling procedures: non-probability, that is non-random, and probability or random sampling. There is a technical definition of probability sampling that I'm not going to repeat here, but for our purposes, we can think of it as random sampling. We'll discuss these procedures at length shortly. Sampling error is the error due to drawing a sample rather than doing a census of the population. We have seen the term earlier in discussing survey research. Sampling error measures the accuracy, or rather the inaccuracy, of the results obtained from the sample. Statistically, you can show that it is a function of sample size and population heterogeneity, that is, variability. The larger the sample size, the lower the sampling error, which intuitively makes sense because with a larger sample, you should have more accurate results. In addition, the greater the variation in the population on the characteristic we are measuring, the greater the sampling error. So this makes life very easy in some ways. That is, if you want to reduce sampling error, we can use two simple approaches. First, we can increase the sample size. Second, we can divide the population into more homogeneous groups, that is, into segments, also called strata, before sampling. Then by sampling from each stratum or segment separately, we can reduce the total sampling error as compared to if we were sampling from the population as a whole. From the above discussion, you may have figured out that sampling error or inaccuracy in the sample results can be large even with a random and representative sample if the sample size is small or the population is heterogeneous. So random sampling is good, but not a magic bullet that can solve all problems. Let's look at some elementary sampling procedures. Let's start with non-probability sampling or non-random sampling. Convenience sampling is the most rudimentary type of sampling possible. It's based entirely on what's convenient for the researcher. This procedure consists of sampling population members that are conveniently accessible to the researcher. Since researchers tend to pick people with whom they share common characteristics, such as co-workers, friends, family members, neighbors, etc., convenience samples reflect the characteristics of the researcher and will not generally be representative of the target population. This procedure should only be used for exploratory research, where getting a representative sample is not an objective. Judgment sampling improves upon convenience sampling in some ways. It aims to ensure that sample members have certain characteristics or meet certain eligibility criteria. For example, we may want to draw a sample of retailers for a survey that have a minimum store size or sales revenue. Again, there is no attempt to obtain a random or representative sample, so essentially it is a convenient sample that meets certain criteria. Quota sampling improves upon convenience sampling by imposing quotas for different groups or segments in the population. This is to ensure that the sample includes all the relevant segments and that its overall composition matches that of the population. For example, we can set quotas for men and women in the sample. Once we fill a quota for a group, we stop sampling from that group. Keep in mind, though, that this is still a convenient sample. Researchers will try and find people who meet the criteria from among those who are most easily accessible to them. Thus, a quota sample may match the population in terms of the desired characteristics, but it will still be a non-random sample. Non-probability sampling procedures have two major limitations, because of which they are typically used only for exploratory research. First, they are very likely to yield unrepresentative samples, so the data from such samples cannot be projected to the target population. That is, we cannot assume that the same results would hold for the population. Second, because they are non-random procedures, it is impossible to calculate sampling error, which is a measure of the accuracy of the results. So even if we believe the sample to be representative of the population, we have no way of knowing how accurate or inaccurate our results are. For these reasons, the use of non-probability procedures should be limited to exploratory research. Let's turn to probability sampling or random sampling procedures. The two most basic approaches in random sampling are simple random sampling and systematic random sampling. Simple random sampling is where every sampling unit has an equal chance of being selected. For example, if we throw names in a hat and pick one or a few names, that would be a simple random sample. While this sounds like it should be a reasonably good sampling procedure, in practice it is not always effective. The main limitation is that it does not rule out unrepresentative samples. That is, because every population member has an equal chance of being selected, there is no way to ensure that the sample will not be skewed or unrepresentative, as shown in the diagram, where the sample comes entirely from one part of the population. For example, if we have 50 men and 50 women in the population, and we draw a simple random sample of 10 people, there is no way to ensure that the number of men and women in the sample will be equal. And in theory, we could end up with all 10 men and 0 women, or vice versa. The second basic random sampling procedure is systematic random sampling. This is a procedure designed to ensure that we sample from every part of the sampling frame. It is useful when population members vary along some characteristic, say income, and we wish to ensure that all levels of that characteristic or income have a chance of being included in the sample. Here are the steps in drawing a systematic sample. We order the sampling frame, that is the list of population members, in ascending or descending order based on the characteristic that we want to have represented. For example, if we are sampling firms and we want to ensure that firms of different sizes have a chance of being included, we would order the sampling frame in increasing order of size from smallest to largest. Then we calculate the sampling interval k, which is the ratio of the population size, that is the number of sampling units in the frame, to the desired sample size. For example, if the sampling frame has 1,000 firms ordered by size and we want to pick a sample of 50 firms, then the sampling interval is k equals 1,000 divided by 50, which equals 20. We pick a random number between 1 and k and use that as a starting point for sampling. Then we pick every kth unit after the starting point until we come to the end of the list. For example, let's say k equals 20, and we draw a random number between 1 and 20 and get 16. So we sample the 16th unit, the 36th unit, the 56th unit, and so on until we run through the list. We will then end up with the desired sample size. Systematic sampling improves upon simple random sampling in that it ensures that we sample from every part of an ordered list. However, it becomes difficult to implement when we have multiple characteristics that we wish to represent in the final sample. For this, we need to use a more complex procedure that we now turn to.